All right, welcome everyone. Today we're going to step into the lecture hall and really dive deep into the world of heaps. We'll go from the classic binary heap all the way to the mighty Fibonacci heap. It's going to be a fun journey breaking down not just what these things are, but more importantly, why they even exist and how they've evolved over time.
So here's our game plan. We're going to start with the why, the core problem that heaps solve. Then we'll get into the nitty-gritty, the classic binary heap, then we'll level up to binomial heaps, and after that, the pro-tier stuff with Fibonacci heaps. And we'll wrap it all up by looking at the whole family of heaps.
Okay, let's get right into it. Before we can really appreciate just how clever heaps are, we've got to understand the problem they were designed to fix. And it all comes down to one thing: priority. So think about this for a second. Picture a super busy hospital emergency room, right? Or even just the CPU in your own computer. How do you decide what gets dealt with first? I mean, a patient with a major injury can't wait behind someone with a sprained ankle, and your operating system needs to handle a critical process right now, not after your cat video finishes buffering. See, this isn't just a simple to-do list. It's a list where some things are way more important than others.
The answer, at least in the world of computer science, is what we call a priority queue. It's an abstract idea, really. You have a bunch of items, and each one has a priority level. Simple, right? But the real challenge, the billion-dollar question, is how do you build one that's actually fast and efficient? Well, that's exactly where heaps come into the picture. They are pretty much the go-to way to implement a priority queue.
Okay, so let's start with the big one, the one everybody learns first. If you've taken an algorithms class, you've definitely met this guy, the binary heap. It's the foundation for everything else we're going to talk about. So what is a binary heap? Well, it boils down to two really simple but super important rules. First, it's got to have a specific shape. It has to be what we call a complete binary tree. Now, all that means is that the tree is filled up from left to right, level by level, with no gaps. The second rule is all about order, and we call this the heap property. And this heap property, this is the absolute magic of the whole thing. Let's say we're talking about a max heap, which is what we'll focus on. The rule is simple. Every parent node has to be bigger than or equal to both of its children. That's it. But that one simple rule guarantees something incredible. The biggest, most important item is always right there at the very top, at the root of the tree. No searching required. Now, here's the really clever part, and honestly, one of my favorite things about this data structure. We talk about it like it's a tree, we draw it like a tree, but we don't actually store it as a tree with all those complicated pointers. Nope, we can represent the whole thing perfectly in a simple array. See? By doing some really simple math, we can instantly find any node's parent or children. This is just brilliant. It's super fast and uses way less memory. Okay, so how do we actually add a new item, a new task into this thing? The process is actually pretty elegant. Step 1, you just stick the new element in the first open spot, which is always at the end of the array. This keeps our tree complete. But of course, that might break the heap property, right? So step 2 is what we call bubbling up. You compare the new guy with its parent. Is it bigger? If so, you swap them. And you just keep doing that, bubbling it up the tree until it's in the right spot. And here's the code that makes that bubble up happen. You can see it right there in that while loop. It's a simple, tight loop. As long as the new element isn't at the root and it's bigger than its parent, we just keep swapping it upwards. It's a beautiful piece of code that perfectly captures that bubbling logic until the whole heap property is restored.
All right, moving on. Binary heaps are great, they really are, but they're not perfect. They have one big weakness, a real Achilles heel. Merging two of them together is a huge pain. It's super slow. So what do? Well, computer scientists invented a new data structure specifically to solve this problem, the binomial heap.
So how does a binomial heap work? The big idea is to stop thinking about one single giant tree. Instead, a binomial heap is like a forest. It's a collection of smaller, very specific kinds of trees called binomial trees. Each little tree in this forest still follows our good old heap property, but the real genius is in how this whole collection of trees is managed. And this right here, this is the payoff. Look at that difference. Merging two binary heaps takes linear time, O of n, which can be really slow if your heaps are big. But with a binomial heap, it's O of log n. That is a huge improvement. And the way it works is just so cool. It's basically like doing binary addition. You just combine the two forests, and if you ever have two trees of the same size, you merge them together to make one bigger tree and carry it over to the next spot. It's incredibly elegant. Okay, but what if your main problem isn't merging? What if the operation you do all the time is updating the priority of an item that's already in the queue? This happens a lot in certain algorithms. For that specific high-performance job, we need to call in the big guns. And that brings us to the Fibonacci heap.
So why should you care about Fibonacci heaps? Well, here's why. They're a total game changer for some really important algorithms. You take a classic algorithm like Dijkstra's, which is used for finding the shortest path in a network. Think Google Maps or network routing. And when you swap in a Fibonacci heap, the theoretical performance gets a massive boost. This isn't just academic, it's fundamental to a lot of high-performance computing. So how do they pull this off? The secret is that Fibonacci heaps are incredibly, well, lazy. They do as little work as possible. Instead of neatly cleaning everything up after every operation, they just kind of throw things into a pile and say, I'll deal with that later. All that cleanup work gets postponed until you absolutely have to do it, which is usually when you extract the minimum element. This gives it amazing amortized performance. It just means that while one operation might be slow once in a while, the average time over thousands of operations is lightning fast. It's a trade-off. You accept a bit of a mess in exchange for incredible average speed. Okay, let's zoom out for a second. We've been talking a lot about binary heaps, right? The bi meaning 2 children per node. But it's really important to realize that the core idea of a heap is much, much broader than just that. We can actually generalize this whole thing. Why stop at 2 children? You could have a ternary heap with 3 children per node. Or, you know what, let's go crazy and have a d-ary heap, where d can be any number of children you want. Now, this creates a really interesting trade-off. The more children you have, the wider and flatter your tree gets. A flatter tree means bubbling up is faster, but the downside is that now you have to check more children every time you bubble down. It's all about finding the right balance for your specific problem. And this table right here, this is really the key takeaway for our entire discussion. There is no single best heap. It all depends on what you're doing. Look here, if all you need is to find the minimum and you're not merging, the binary heap is simple and its O1 getmin is great. But if you need to merge things constantly, the Fibonacci heap's O1 merge is unbeatable. It's the perfect example of a classic engineering trade-off. You have to pick the right tool for the job.
So when you look at the whole journey from binary to binomial to Fibonacci, you see a really beautiful story. It's the story of computer science itself. You identify a problem, a bottleneck, and you invent a clever new solution to smash through it. It really makes you wonder, doesn't it? What are the big performance bottlenecks we're facing right now? And what amazing, elegant new data structure is some student in a dorm room about to invent that will solve it?